And so we're starting here today by checking to make sure that you remembered how to graph each of the 4 parent functions that you've seen so far this year. The reason is because I'm going to be giving you a whole new function type today, and I always like to make sure that we remember what the others look like. One other thing though that's worth mentioning here, I don't really need to plot a ton of points when it comes to the ones that are straight, right? I can plot a couple points and then break out the ruler. But when it comes to the curves, we really have to plot every point that's going to be on that curve so we can actually draw the curve in nicely. Otherwise, if we just plot 1 or 2 points and then just kind of rough it in from there, we end up with something that doesn't really look very good. We tend to be like, okay, I got those 2 points, so then it goes like that. Well, it's kind of right, but also not. You know, the shape is kind of there, but it doesn't really represent the actual numbers that are involved. And the work that we're getting into today, and the graph we're doing today, you're going to see the actual numbers are going to be pretty darn important here. They change the whole complexion about what a graph is looking like compared to some of the other ones. Now to start getting us into the right mindset for this, here's our starting problem. If you have $1 now, and it doubles every single year, what equation would represent the amount you have after X years?
That would be,
well, year 1 we have $1, right?
1x to the second.
So after 2 years, I'd multiply it by 2, right?
No. Yes.
So that's after the first, so after 1 year we multiply it by 2, we got that much. After 2 years, I'd multiply by another 2.
So you'd have an x as the next one.
And then another 2. Every single year I add another 2 on there, right?
Yes.
Yep. So it'd be like a y equals 2 to the x. Again, remembering, of course, that anytime I'm multiplying the same number by itself a certain number of times, it gives us that. What I wrote up there, that was 2 to the 5th, because I wrote 5 of them. Why did I write 5? Because I didn't want to write another one. Because it just keeps going and going for X years. All right, so this basically means that this is the type of equation that we've been working with recently a lot. It's also the equation that we're going to be graphing today. So above your next graphing grid, write that equation. Y equals 2 to the power of x. All right, and since this is a brand new function type, I'm going to make a table of values to know what this graph is really going to behave like. So let's start grabbing some numbers. Now I'm going to choose some numbers that are very easy at the start. So let's just start with 1. If x is 1, what is y? So like if I plug 1 in for x here, what's 2 to the power of 1? 2. Okay, so that's going to tell me the point 1, 2. Go ahead and plot that point 1, 2. Okay, now I'm going to go to the next x. I'm going to go to x being 2. If x is 2, what is y? 4, because I'm doing 2 to the power of 2. 2 squared is 4. Okay, so that again gives me a point that I can now plot 2, 4. And notice it's actually a coordinate pair. It's not like I start at the last point and go 2 and then 4. It's actually the coordinates. X is 2, y is 4. All right, next one, I'm going to go to x equals 3.
6.
So that means I'm plugging 3 in for x here. So we're doing 2 cubed. That is 2 to the power of 3, which means I'm doing 2 times 2 times 2.
It would be 8.
Which is 8. Yes. And so that gives me 8. Again, another point that I can plot. So you plot the coordinates 3, 8. Notice there's actually a nice little pattern since I am just multiplying by another 2. So like when I go to do x is 4, that just means I'm multiplying by 1 more 2.
So 8.
Well, that's like taking the 8 that I just found and multiplying it by 2, which is 16, yes. And by the way, notice, yes, if I actually plug that 4 in for x there, 2 to the power of 4 will give you 16 on your calculator as well, if you wanted to do it that way. Now, though, in this case, I can't plot 416. It's off my graphing grid. So that's where I'm going to stop on that side. So I already know those points. But all that tells me is that my graph is doing this. I don't know yet I'm going to find out soon. I don't know yet what is happening on the left of it. I mean, is this going to be like it's a U-shaped graph, or what's it doing? So, I'm not going to start going the other direction. Now notice I started at 1, because sometimes plugging in 0 is tricky for people. What is 2 to the power of 0?
0.
It's not 0. Let me give you a way to see why it is what it is. What if I were counting backwards here? Because it's kind of like I'm going 4, 3, 2, 1, 0, right? Okay, so I'm going up this list. So if I start at the 16, go to 8 to 4 to 2, notice that's like I'm dividing by 2 each time. What's 2 divided by 2?
1.
1. 2 to the power of 0 is actually 1. So I'm going to plot the point 0, 1.
What the frick? So it just goes over like this?
Alright, so now that was dividing by 2. Now, what if I go down to -1? It's like I'm dividing that by 2 yet again. So if I put the numbers in the right order here, I can kind of see maybe a little bit more easily how these patterns are working out. So now I can actually follow this. So 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. What's 1 divided by 2?
What's 1 divided by? -1. -0.
1 divided by 2 would be a half. Or, if you did it on your calculator, 0.5. They, of course, are the same thing, right? So that now gives me the point. X is -1, y is 0.5. Or 1/2 if you prefer. And yes, I'm actually plotting that decimal point. That partial. And so we can actually keep following that same pattern where as we go up this table where it's like we're dividing by 2. But just to bring in a different way of looking at it, because we're going to hit some numbers that maybe are a little bit trickier for you to think about that way. Break out your calculator. Let's actually plug this -2 in for x in our equation. So that means I'm going to now do y equals 2 to the power of -2. Now if you did it right, you should be getting an answer here of 0.25. Alright, and now that I have that 0.25, I can go ahead and plot that point on my graph as well. So I go to -2 on the x, and up only 0.25. It's not up very far, is it? Now, sometimes people end up saying, wait, how do I do that? How can I be precise? Well, you can't be perfect, but I'm not expecting perfection. I'm expecting it to just be close here. Get as close as you can to 0.25. And also notice that still holds our pattern. If I took 0.5 and just divided it by 2, it would give me the 0.25 as well. I could do the same thing with the -3. That would give us 0.125. So let's plot that point. So I go to -3 and then up just 0.125, up even less.
And then less than a penny.
So notice what's happening here as I'm going to the left, and I'm actually plotting those points. Because I really want you to think this through here.
Oh yeah, look, it looks like a L.
As I'm heading over here, it's cutting it in half every single time I go to the left. And so these points that are down here, this height gets cut in half. This height will get cut in half. This height gets cut in half. And it just keeps getting cut in half more and more. Now as I'm out here, am I ever going to hit a number where when I cut it in half, it gives me 0?
No. Possibly. No.
No. Because you can't divide 2 whole numbers and get 0. The only way you can get 0 with division is if you do 0 divided by something. And if we can't hit 0 in the first place, I can't get 0. And so if it never hits 0, it's not going to cross into the negatives either. Because you're never going to do a positive divided by 2 and get a negative. It's impossible. And so to finish making this graph, I'm not actually going to go through and calculate every single point here. Because I'm now so close to the axis that I can basically just estimate, okay, getting closer, getting closer.
Essentially just right on.
Yeah, and at a certain point, basically, you just are hitting the axis because it's so close. We can't differentiate between it being, just a tiny, tiny fraction above the axis or on the axis. So we just get as close as we can and plot those points. And then go ahead and draw your graph through those. So notice what this curve does.
It makes an L. Okay.
This curve here, on the left side, it's basically on the axis. It's gotten so close to it that it looks like it's actually hitting it. But notice, remember I'm saying, it looks like it. Remember, it never actually hits 0. It just gets so close to it that we can't tell the difference visually. But then as we go to the right, my height is doubling every time. And so 1/2 became 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. And 8 times 2 gave us the 16, which didn't fit. And that's how we can actually get these graphs, is as I go to the right, I'm multiplying by my base. I'm multiplying by, in this case, 2. Now, this type of graph, where we have the number to the power of x, this is the exponential function family. So when we talk about exponential equations, this is the sort of thing that we're looking at when we go ahead and graph it. Now, again, we're doing something similar here. I'm going to go ahead and make the table again, just so we can, again, see how this thing's behaving. And I'm just going to plan ahead right now. I'm going to go ahead and plan for going into the negatives and, of course, into the positives, where numbers tend to be a little bit easier. But the first values I'm going to find are going to be the easy ones. So let's start down when x is 1 here. When x is 1, that means I'm doing 3 to the power of 1. What is 3 to the power of 1? 3, because anything to the power of 1 is itself. So that gives me the point 1, 3. Okay, let's go to 2 now. What is 3 to the power of 2?
Dead. That's
9.
right.
It is 9. It's not 6, because remember I'm not multiplying by 2, it's 3 to the power of 2. So 3 times itself 2 times, so that's why it's 9, 3 times 3. So that means x is 2, y is 9.
27.
Plot that point. The next point, if x is 3, 3 to the power of 3, that's actually multiplying the 9, the last one I got, by another 3. That gives me 27. Okay, we're now off the grid, so I'm not even going to bother with the 4. And so, since it's off the grid there at 4, I know already I'm just not worrying about it. So now that I did the easy positives, now I'm going to start working up from there. What is 3 to the power of 0 going to give me?
2.
Well, what was 2 to the power of 0 again? 1. 3 to the power of 0 is also 1. Which, again, I could kind of reason through the same way, because if I'm going up through here, it's like I'm dividing by 3. 3 divided by 3 would give me 1. And actually, 1 divided by 3 is going to give me my next y value up here at -1. Or I could actually plug it in my calculator. I could do 3 to the power of -1, and it would tell me 1/3 or 0.3 repeating. Okay, so let's plot those points here. I forgot to plot the 0, 1, so I'm going to go ahead and do that. Then I'm going to plot the -1 and the 0.3 repeating, although personally, I think of it as 1/3. I find that easier to think of it as -1 and 1/3. Because that way I just remember that as I move to the left, it's always 1/3 of the last height. It's like I'm dividing my height by 3. But I could also do it by plugging in the points as well. So like I could plug in now the -2, 3 to the power of -2, in the calculator. That's going to give me 0.1 repeating. Or if you prefer the fraction, that's actually 1/9. 1/3 of 1/3. And you know, honestly, that is so close now to the axis that I'm not going to be able to be much more precise. So again, I'm just not going to worry about the -3 because it's so close to the axis. The actual decimal isn't going to be super important. So then as I go to the left then, I am just going ahead and I'm dividing each of my heights by 3 until I'm basically on the axis. Now this is our next one that we're doing here is the 0.5 to the x. This is usually the point where all of a sudden it was like, Yeah, that 2 to the x, that's fine. 3 to the x, that's fine. 0.5 to the x, why do you hate me? Well, I just want to actually give you the tools to know how to handle this. Once again, just so we can kind of approach it from the same kind of perspective, I'm going to go ahead and make a table. And I'm going to think about what would the numbers in that table give me. Now, because this is a decimal to the power of x, it would make sense that we're probably just going to do a lot of calculator work here. And that's basically what it's going to mean. So, actually, I'm going to start with one which hopefully actually by now might be the easy one. If x is 0, what is y? Well,
0.5.
2 to the power of 0 was 1. 3 to the power of 0 was 1. 0.5 to the power of 0 is
X.
1.
It's still one. I was
It's still 1. Because any number to the power of 0 is 1. Okay, well, and we also saw 2 to the power of 1 was 2. 3 to the power of 1 was 3. So what do you suppose 0.5 to the power of 1 would be?
1.
5.
It'd be 0.5. Because anything to the power of 1 is itself. So I can know that's going to be the 0.5. I would expect you to be able to know those off the top of your head, because those are rules that are true 100% of the time.
0.5.
Now, we got to get into the slightly tricky ones now, because now I come to x being 2. Well, that means let's go ahead and plug in the 2 here. Let's do this. Break out the calculator, do 0.5 to the power of 2 and see what that gives you. All right, and when we do that on the calculator, you should find that 0.5 to the power of 2 is 0.25. Okay, so I go ahead and plot that 0.2 and 0.25. I can do 0.5 to the power of 3 now. 0.5 to the power of 3
35.
gives me 0.125, which is getting even closer to the axis. Maybe you're already seeing what's happening over there, but if not, let's go ahead and deal with the negatives, and that might make it even easier to see. So again, calculator time. 0.5 to the power of -1. And when we do that 0.5 to the -1, you get 2. You'd think that something that looks so messy would look more complicated and give you a more complicated answer, but it doesn't. Well, I suppose we can be grateful that it doesn't, right? But let's go ahead and plot that point then. So I got -1, 2. So x is -1, y is 2. Plot that point. We repeat the process. We go 0.5 to the power of -2. If we do that, that gives us 4.
I'll copy mine.
And then we do 0.5 to the -3. And we do that calculation, that gives us 8.
Damn.
And so
Alright.
notice,
Oh God, what if it's a negative point? What if it's
Well-
y equals negative?
now having plotted those, did you notice anything familiar about this?
It went backwards, then the last one?
Yeah,
I mean,
compare this to the work, even compare it to the graph you made for y equals 2 to the x.
it's just a flip.
You notice it's the exact same thing, except 2 to the x went this way. It hit all the same points, just it was on the other side. I'm not going to get into all the details on it, but it's actually because 0.5 to the x is the same as 1/2 to the x. And 1/2 to the x is going to be very closely related to 2 to the x when x becomes negative. So there's some interesting little tricks and things that happen in there as well. But whenever you have to graph one of these, you just look at that base, whatever that base is, and unless it's a super easy one, just plug those into your calculator and see what those values are. When you get down to this end, where the numbers are basically on the axis, just plot them as if they're on the axis and finish the pattern.